Oi. Oh, I've still got my headphones in. What the heck?
Tagon.
Ugh, so, it's a nice day outside, but it's kind of cold and kind of windy, and I'm not feeling too hot. But with consistent diet and exercise and math, I can stave off whatever head cold the world is trying to throw at me at the moment. So, I figured I sound a bit drab and I don't feel very well, but I figured since I'm indoors, I may as well make the next video. This might not help my ability to get better, but Joe is with me. Whatever the that was. So, we're obviously going to continue this path down the harmonic numbers. I'm going to edit out all of these pregnant pauses because darn, am I taking a while. Except today, we're going to do a thing about sums over the harmonic numbers, like adding up harmonic numbers, not the numbers that make the harmonic numbers, right? Like I said I would do in the last video. We're going to do that, and we're also going to take a look at one of the sum representations that I did in the last video and see that we can actually derive another integral representation for the harmonic numbers using something a little exotic. And all of these little clues that I'm showing where the harmonic numbers are equal to this thing or they're equal to that thing in a very subtle way is all going to come to fruition when I finally drop my next generalization bomb upon the response of the mortal enemy in this battle that I've gotten myself in, which I hope is responded to soon, Papa. So it's going to be a very strange relationship between the harmonic numbers and a different kind of zeta function that we're going to see. And hopefully all of these little clues and like people that are watching can see I'm going where I can sort of finally generalize a function that is the harmonic numbers over all the complex numbers. We're also going to do just a little separate explanation as to why the negative integers might not be valid for the harmonic numbers, because it's almost the same as why the factorial function doesn't take negative integers. So, with all that out of the way, let's do some math. Sorry I'm a little low energy, I'm just feeling like crap. Okay, so after that long and drawn out intro, let's actually get to business. So, get down to business, I mean. Okay, so what are we going to be investigating today? I remember mentioning at the end of one of the recent videos, that I plan on eventually answering this question. What is the integral over the harmonic numbers from 0 to n? And this is the next generalization that I plan on doing after we recognize that going from 0 to 1 is actually equal to the Euler-Mascheroni constant. Say that if n is 1, if I replace it with 1, we know that this is equal to the Euler-Mascheroni constant, right? So that was demonstrated in a previous video. But today we're not going to be considering the integral from 0 to n of the harmonic numbers, we're going to be considering the sum from 0 to n of the harmonic numbers. Now this may seem like an odd question because the harmonic numbers are themselves a sum. So let's write out what these first few terms are going to be. So at k equals 0, we have the 0th harmonic number, which is equal to 0, right? If you're not adding anything, you get like the empty sum. And it's not surprising that that falls out of the math, right? Sort of like how 0 factorial is 1. The next harmonic number, the first one, is just 1, right? The reciprocal of 1 is 1 over 1. The next one is 1 plus 1/2, which is 3 halves. The next one is 3 halves plus 1/3, which is 11 over 6. And those sort of just keep on going. And so the nth term in this sum is just going to be adding up the first n harmonic numbers. Since the first one is 0, we can actually start this sum at 1, of course, and go up to n of h of k. But instead of listing them out as the harmonic numbers, I'm going to list them out in a particular way that's going to allow us to sort of make a closed form expression for this that's also going to be in terms of harmonic numbers. Because what is the first harmonic number? The first harmonic number is just adding up the first reciprocal of the natural numbers, which is just 1. And I'll write it as 1 over 1, because that's sort of the perspective that I'd like to have. The next harmonic number is the first reciprocal plus the second one. So we're going to get 1 over 1 plus 1 over 2. The next one, the third harmonic number, is the sum of the first three reciprocals of the natural numbers, and that's plus 1 over 1, plus 1 over 2, plus 1 over 3, and then we just keep going all the way down to the nth harmonic number, and we end up with 1 over 1, plus 1 over 2, plus 1 over 3, plus ... plus all the way up to 1 over n. And you'll notice we have ourselves a nice triangle of sums here. And how many steps are there in this whole thing? There are n steps, right? Because I'm adding up the first n harmonic numbers. And because each one is got one more term added onto it, you can see that each term in these series is being added one less time than the one previous. So, as we can see, there are n ones, right? Because there's n steps and each of them contain 1 over 1, so this whole sum right here is n times 1, or n, right? But I want to write it in actually a particular way. I'm going to write it as n minus 0 over 1. Notice that that's exactly equal to n, right? Because n minus 0 is n, and n divided by 1 is n. But I'm going to write the next one, which is the sum of the 1/2s. Notice that there are n steps, but the first one doesn't have 1/2. So it's actually n minus 1 times 1/2. So we have n minus 1 over 2 for the sum of all the 1/2 pieces. I hope that's clear. Notice that the 1/3s don't start until this third term, so they are missing, so there's n steps, but the first two don't have any thirds, so it's n minus 2 times 1/3, right? And if we keep adding all the way up, you'll notice that we're taking one less away from the n in the numerator than the denominator is. So if the denominator of this is n, then the numerator has to be n minus 1, right? Because that is one less than the denominator. And you can see that there's always one less term than the number in the denominator, right? There are n ones, there's n minus 1 1/2s, there's n minus 2 1/3s, there's n minus 3 1/4s, all the way down to n minus 1 1 over n's, right? And so we can sort of write a sum based on this, right? If this is the series that we're talking about, we can sort of run these numbers as an index, right? We can write them as the sum from k equals 1 to n. Well, the denominator is going to be k, right? Whatever k is in this state, because we're going from 1 to n, right? And the numerator is just going to be n minus k minus 1, right? Where k minus 1 is like in parentheses, so we get n minus k minus 1. I hope that's clear, that that's what we've been able to get by simply adding up columns of terms instead of the rows of terms. And we're actually going to use this method of summing things up to get another really, really neat value for the nth harmonic number. For the Euler-Mascheroni constant at some point as well. So stay tuned for that. So notice this term right here, right? We distribute this -1 in and we get n minus n plus 1, which does in fact simplify to just 1, right? So we are going all the way from n down to 1, and the denominators are going all the way from 1 to n. So I hope that's clear as to what's happening here. We're sort of switching the spots for the numerator and denominator as we go all the way down. It's actually quite a cool little sequence. And so now we're going to evaluate this sum. So I'm going to erase all the steps in between. I hope this is clear what I've been able to do, and I'm going to write this up there. So we've just arrived that the sum over the first n harmonic numbers is also equal to the sum from k equals 1 to n of n minus the quantity k minus 1 all over k. Right? That's what we've just been able to derive. But now what we can do is, because this is always a finite sum, because n is just some fixed integer, we can break this up into 3 different pieces. We can do n over k, negative k over k, and 1 over k. So that allows us to write this as 3 separate sums from k equals 1 to n of n over k minus the sum from k equals 1 to n of k over k, right? The minus, I've just carried out the minus to the front, plus the sum from k equals 1 to n of 1 over k. So I've simply broken these 3 things up into 3 separate sums. And we're just going to evaluate what each of these things is. Notice that this n is just the upper index, but doesn't depend, is a fixed value, so it doesn't depend on k at all. So I can factor it out, and I get n times the sum from k equals 1 to n of 1 over k. K over k, since k is never 0, this is always 1, right? K over k is always 1. So we're just getting minus the sum from k equals 1 to n of the quantity 1. And this will just remain the same, the sum from k equals 1 to n of 1 over k. But notice what we have here. We have 2 representations of the nth harmonic number right there. So it's n times the nth harmonic number. And this one is also the nth harmonic number, right? By definition, it's summing over the reciprocals of natural numbers from 1 to n, so that's the nth harmonic number. And what is it when you just add a bunch of 1s from 1 to n? Well, this sum here is just equal to n, right? 1 doesn't depend on k, so you're just doing 1 plus 1 plus 1 plus 1 plus 1 n times. So this is just n minus n, right? And now take a look what we can do. First of all, we can factor out the nth harmonic number from these 2 things, and we'll end up with I guess I could write this step over here. We can factor out the nth harmonic from both of the nth harmonic number from both of these things and get n plus 1 times the nth harmonic number and subtracting n. So this right here is already a pretty neat form because we've got it in terms of the nth harmonic number, but because this sum already contains the nth harmonic number, we're going to want to differentiate it somehow. Not differentiate in the calculus sense, but make it seem different. So what we can do is actually shift this up to the n plus first harmonic number. What would that mean to go from the nth harmonic number to the n plus first one? That means we have to add the quantity 1 over n plus 1, right? 1 over n plus 1. If we're adding the quantity 1 over n plus 1 here, that's also being multiplied by n plus 1, right? So here, I'll write it out so that it's more clear. So we have n plus 1 times h sub n plus 1 over n plus 1. Now this is n plus first harmonic number, right? Because adding the next reciprocal is how you get to the next harmonic number. But I can't just add this without subtracting it somehow, because then I would be changing the value. So I'm still going to subtract this n out the front. But notice, if I'm adding 1 over n plus 1, and then I'm multiplying by n plus 1, adding this term in here is actually equal to adding 1 to this quantity, because think about it, n plus 1 divided by n plus 1 is just 1. So to balance this out so that I don't actually change its value, all I have to do is subtract 1 on the outside. But this in here is the n plus first harmonic number. And this is just negative 1 times n plus 1. So I can rewrite it like so. N plus 1 times the n plus first harmonic number minus the quantity n plus 1, right? Because this is negative n minus 1, factoring out the negative 1 gives you that. But now we have a common factor of n plus 1 in both of these things, so I can factor that out as well, and we end up with our almost pretty much final result that the sum over the first n harmonic numbers is equal to the quantity n plus 1 times the other quantity, the n plus first harmonic number, minus 1, which is quite a nice result. And so that's the first thing I wanted to show you in this video. Isn't that very cool? The sum over the first n harmonic numbers is equal to n plus 1 as a quantity times the n plus first harmonic number minus 1. Very, very neat. What this also allows us to do is solve for the n plus first harmonic number in terms of the other harmonic numbers below it. So it's sort of a recursive definition in a sense. So all we have to do is write this up there, and I will show you what I mean. So we've also just derived now that this is in fact equal to n plus 1 times the n plus first harmonic number minus 1, right? That was our result. So this is the sum over the first n harmonic numbers. Very, very neat. What this also allows us to do is solve for h sub n plus 1 in terms of a sum over all of the other harmonic numbers beneath it. So we can simply divide by the quantity n plus 1 and then add 1 over. So we get, this implies that the n plus first harmonic number is equal to, we're going to end up with 1 over n plus 1 times the sum over the first n harmonic numbers, and then we're adding 1 over to the other side after we've divided, so we get 1 plus that. And so look what we have. What I'm actually going to do now is I'm going to plug in n minus 1 for n, so that we actually end up with a formula for the nth harmonic number as opposed to the n plus first one, because I think that's more illustrative. So we end up with n minus 1. And so all this is saying is that to get the nth harmonic number, you just have to add up the first n minus 1 harmonic numbers, divide that sum by n, and then add 1. And that's how you get the next harmonic number. It's a very nice recursive definition of the harmonic numbers. So as soon as you start off with h sub 1, the first harmonic number is 1, then you can define all the other ones based on that. And it's a very, very nice result that I think is quite a lovely thing. Quick little thing, this channel has an Instagram, so it is at whatthehectagon, of course, and it has a Twitter, and it is of course naturally, also at whatthehectagon, and my email is the incorrectly spelled whatthehectagon, why spell check before you make the email right, that you can't then change, at gmail.com. Now all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. That's the stuff. Thank you for watching, and bye-bye.